All right, so I think we can start. So I'd like to give you a warm welcome and thank you for joining us for this online event on retrofitting and circularity in the metal making industry. It's organized by 3 EU-funded projects, namely RETROFEED, Initiate, and REVamp. My name is Claire Chrétien from EIP. We lead the communication and dissemination work package for RETROFEED. Before we jump into the topic, I would like to give you a couple of information regarding housekeeping for a smooth meeting. So your microphone should be muted and your camera off by default, and please make sure it remains that way for the whole duration of the meeting. If you have any questions, please type them in the chat. We will take questions after each project's presentation and also at the end after the panel discussion. The event is recorded. Only the speakers and moderator will be appearing on the video if you keep your camera off, and the recording and slides will be available afterwards on the project website. So thank you for your attention. It's now time for me to hand over to our first speaker, Jean-Théo Ganda from Eurofair, who is Director of Technologies. So please, Mr. Ganda, the floor is yours.
Thank you very much, and thank you for inviting me, and good morning, everyone. So transforming the metal making industry, that is the introduction to today's discussion and exchanges we will be having. So would you help with showing the slides?
Of course. Just 1 second.
Next slide. So a short introduction on the European Green Deal. The European Green Deal has been presented in December 2019. It's the European growth strategy to make the EU economy more sustainable. The overarching objective is for the EU to become climate neutral by 2050. And the core of the implementation activities in the frame of the European Green Deal is the European Climate Law. And this European Climate Law turns the 2050 climate neutrality objective of the EU Green Deal into legislation. So now they have also defined a milestone toward these targets. So it's a target for greenhouse gas emission reduction in 2030. That should be at least a reduction of 55% compared to 1990. Now, the European climate law requires that all the European policies contribute to achieving this objective of the EU Green Deal. Therefore, the European Commission has been reviewing all existing policies and union legislation to ensure that there's a good alignment of the 2000. They are good aligned with the new 2030 target and the climate neutrality objective of the EU Green Deal in 2050. This exercise is being done in a frame called Fit for 55 package. Next slide, please. Just to give you an idea of so what is being done there. Here we have a list of some selected initiatives that is relevant for manufacturing industry. It's a long list. Here only some initiative. For example, in first bullet point, we can see the revision of the emission trading directive that has been done. We have the revision of the energy efficiency directive. We have the energy taxation directive, then the proposal for a carbon border adjustment mechanism, and that will start in October here. First of all, for a transition period. And then we have also very important the circular economy action plan. And then maybe when you have the time, you can go through the list. Next slide, please. Now, when we talk about decarbonization of the European metal sectors, We know that those sectors have been already decarbonizing. But if we look at the objective of the EU Green Deal becoming climate neutral by 2050, this will require deep carbon emissions cut. And this deep carbon emissions cut can only be possible through new technological pathways. Now, if we analyze the different pathways that is being considered in the energy intensive industries, including in metal making sectors, we can group those pathways in 3 blocks. The first one will be continuing with using fossil carbon, but making sure that we use less and less. That is what we call smart carbon usage that we can do. We can achieve through process integration. That is here through making the process shorter, and we're using internally the process gases, or we can use also carbon capture and usage. Both process integration or carbon capture usage can also be combined with carbon capture and storage. The second pathway will be just to avoid using fossil carbon. How do we do that? This is via using directly electricity or using hydrogen to replace carbon. The third pathway will be then circular economy approaches. Here, the idea will be to enhance the recycling or the reuse of residual materials, for example, scrap or slag or dust, and also increase the use of residual energy. That will help us to increase resource efficiency. Now, if we consider all these pathways, be it climate circular economy or smart carbon usage using, for example, carbon capture and usage, those gives us very good opportunity for synergy between different industries or different sectors. Next slide, please. Here I give an example how we apply it. Here that's for the steel industry. This is here, we show here that we have projects, some key projects here for low CO2 steel making. We see that we have different projects across Europe, and then also touching on the different pathways that we have just shown. In the steel industry here, we have summarized 60 projects. Those are only the projects that have a tier level of at least 7, and that will start before 2030. Some will already start in 2025 to 2026, and they have the potential of reducing the CO2 emission yearly by around 81 million tons. So that is over 1/3 of the current direct and indirect CO2 emissions of the steel industry. So the transformation will cost a lot of money. We are talking here about capex needs of about 1 billion, and opex need for the next 10 years will be about 44 billion euros. Then we will need a lot of energy. Here, for example, we need for the steel industry alone, we need about 165 terawatt-hour electricity in 2030. If hydrogen will be produced via electrolysis, for this hydrogen, we will need 90 terawatt-hour to produce 2.12 million tons. And then the rest will be 75 terawatt-hour for driving the processes. Now, if we look at 2030, next slide, 50, next slide, please. In 2050, the steel industry will need 5.5 million tons of hydrogen. If all this hydrogen will be produced via electrolysis, this will translate into a need of 234 terawatt-hour electricity, and then also we will need about 162 terawatt-hour for driving the process, bringing the total in about 400 terawatt-hour per year in 2050. That is a lot. That is about 7 times than what the sectors purchase from the grid today. So, and then on top of this, we'll need also to store about 21 million tons of CO2 yearly. Next slide, please. Now, if we look at the metal industry in general, we can say that the transition to a net zero economy will be really metal intensive, and metal sectors will be key enablers for this transition to circular and climate neutral economy in Europe, and it will be essential for the European strategic autonomy and resilience. We will need big quantities of metal for the necessary transition of our energy system. This in order to achieve the EU Green Deal objective. Here you can see the result of an analysis made by McKinsey, based also on a study made by GRC, that is the European Commission, and then also based on a study made by the IEA. What we can see here that, for example, steel, copper, and aluminum will be really needed for this transition. Next slide, please. Now, what are the key drivers? So we need some key drivers to ensure really competitiveness, and then to spur the transition of metal sectors. One thing we need, very important, is to have access to sufficient and affordable CO2-free energy, and then also access to affordable primary and secondary raw material, for example, scrap. Metal scrap will be very important. And then second thing, what we will need really a better tailored funding and financial incentives across Europe, including the establishment of lead markets for green products, or in general for CO2 low products. The third thing we will need a level playing field with global competitors, and this one, how we can achieve that is through effective EU trade policy, and this is in order to ensure an open and fair trade, and that includes, for example, the continuation of the EU steel safeguard. That is very important safety net. That includes also solutions that secure exports under the carbon border adjustment mechanism that is meant to replace progressively free allocation in the frame of the European emission trading scheme. Very important also, what we need is to mainstream industrial policy and competitiveness in all the plan or ongoing policy initiative and legislative proposal. Competitiveness will be key. We need to make sure that we can keep industry competitive, so that we can keep it here, because it's about sustainable economy. So we need not only to look into the objective of protecting environment, we need to look at also the aspect of economy, competitiveness, and the third aspect will be then the social aspect, securing job in Europe. So those are the words that I've tried to summarize in order to introduce the discussion that we'll be having today. If you have further questions, please ask, or we can discuss later on. Thank you very much.
Yes, thank you very much, Jean-Théo Uganda from Eurofair for this setting the scene presentation. I would like now to proceed to introducing the three projects that we present their solution, starting with REVamp. So Bernd Klein, the project coordinator, will present the project now. Bernd, the floor is yours.
Mm-hmm. Thank you, Claire. I would like to share my presentation. Okay, can you see it? Okay, thank you. So yes, thank you very much, Claire, once again. So I will present the project REVamp, retrofitting equipment for efficient use of variable feedstock in metal making processes. And Today I will focus on a very important part of this project, which is the characterization and intelligent use of metal scrap. So I myself, I'm department manager at VTH Betriebsforschungsinstitut in Düsseldorf, Germany, leading the department measurement and automation of steelmaking processes. And I'm also the coordinator of this REVamp project. So what are the objectives of our project? So the main challenges which we are facing in metal making is that we have to cope with a variable material feedstock. So metal scrap is changing a lot in their properties, and also the properties are becoming worse during the time as also the quality of the steels of the metal scrap is becoming worse, including more tramp elements, and so we have to cope with this challenge. Also, we have to use alternative energy sources for running the processes, for melting the scrap, and we have to operate these melting plants also with maximum efficiency. So the objectives were then to develop tools to characterize the different metal scrap materials and to set up a charge mix optimization for these scrap materials, to preheat scrap also with alternative fuels, then optimize the energy mix and the furnace operation. And this is done also by process models being used for offline simulations, but also for online process control. So methods being used are new sensors, new equipment, especially for scrap preheating, enhanced process models, optimization tools, decision support systems, leading all to better process monitoring and control. So in this project, we have 3 demonstration cases. The first one is steel making, the second one is aluminum production, and the third one is lead production. And the expected results are an improved resource efficiency, improved energy efficiency, increased productivity, and improved and constant quality. So here I show you some of the tools which are applied in this project. So first of all, we have to analyze the material and energy feedstock which is used for metal making processes. Then we will develop scrap preheating equipment, and in this presentation today I will focus on the sensors and models for feedstock characterization. And on the other hand, we have, of course, a lot of process models being applied, which are material flow analysis, analytical and statistical process models, energy efficiency models. And these models in combination then with the sensors are used for charge mix optimization, monitoring and prediction of process behavior, and also model predictive control. And all the tools are then accompanied by evaluation of KPIs and life cycle analysis. So the partners in the project, we are 16 partners, focusing each of them on different parts of the metal making industry. So we have, as I said, the 3 use cases. And also we have some partners providing the sensor technologies. I will explain this in more detail in my presentation. And also partners developing the process models and the scrap mix optimization tools. So what is scrap-based metal making? What is the background and the approach followed in the REVamp project? So as I said earlier, the properties of the charge materials for metal making play a very important role for process performance and also for achievement of the target qualities. But these properties are changing a lot. They are varying over time. They are varying from batch to batch sometimes. So it is important that we have an optimal charge mix for the melting furnace, which has to be determined for each produced quality, considering especially the composition, the metallic yield, and also the costs of the different scrap types. And to assess the properties of the different metal scraps, we have to apply appropriate inline sensors and also statistical calculations so that we can track the scrap properties during the time. And also we have to control the melting processes and to adapt this control to the properties of the actually charged scrap types so that we can produce the metals in an energy and resource efficient way. So we have defined a kind of closed loop control system for this purpose. And I will now go into detail for each of these parts of this loop. And I will start with the determination of scrap properties based on statistical analysis. So as I said earlier, the relevant properties of metal scrap are the metallic yield, the chemical composition, and the required energy input for meltdown of the solid scrap to produce a liquid metal melt. So input data for statistical analysis are then on the one hand side, the chart scrap types for each melt, and then the achieved liquid metal weight and analysis for a larger amount of heats. So from this databases, you can determine the chemical composition and also the metallic yield of each scrap type in use, of course, with a certain uncertainty. As I said, the properties of these scrap materials are varying a lot. And as you can see here from these nice Violin diagrams, that for some scrap types, you have a very large scatter in the different element contents. So what we did, especially for steel making, but also for the other metal making processes, we developed software tools to provide a comprehensive overview on the analysis result of regarding the different scrap properties. You can see here, for example, the tracking of the copper content of certain scrap types over the time, or you can see evaluation of the required meltdown energy for the different scrap types. So next is the analysis of the scraps by means of inline measurement technologies. So we applied two different technologies. First of all, for surface analysis, we applied the so-called LIPS technology. So LIPS means laser-induced breakdown spectroscopy. And here the principle is that a short laser beam pulse evaporates and excites a small amount of material at the surface of the scrap, and the spectral lines in the optical emissions are collected and analyzed to determine the elemental composition of the metal scrap. So we have applied this LIP system for all three use cases. And for aluminum and lead containing metal scrap, we have performed this analysis on placing the material on a conveyor belt. You see here an example with the aluminum chips, that is small parts of aluminum scrap, which can be analyzed in a continuous way by applying the slip system. You see here the laser beam with the blue light on this picture here. And with this system, we can analyze the composition of the different scrap materials and also to indicate where, for example, for aluminum, certain scrap particles have a higher content, for example, of copper or other elements. So for the for the steel scrap, the application is completely different. So here we will mount the lip system on a gantry to scan the scrap surface of a truck loading at the entrance of the scrapyard. That means the truck enters the scrapyard, and the lip system will then scan the whole surface of the scrap load in the truck to have a complete view on the composition of the metal scrap being delivered to the plant. So next part is the bulk analysis of the metal scrap. With the lips, we can only analyze the surface, but with this nutrient sensor, which we have developed, you can analyze the complete volume of the scrap. So the technology which is used is the so-called nutrient activation analysis. And here, in this case, nutrients emitted from a source, which can be isotopic source or a nutrient generator, interact with the tested material, exciting its nuclei, and these emit characteristic gamma radiation, which is recorded by means of scintillation detectors, and they are converted then into an energy spectrum, which can be analyzed by means of machine learning methods to allow the determination of the material composition. So you see here on the left-hand side a system where we can analyze the composition of the aluminum chips, the aluminum scrap. So the sensor is mounted here in this closed loop cycle of the material, and the scrap is then fed by this elevator system and is going through the nutrient scanner, and the analysis is then displayed continuously on the screen to follow the composition of the different scrap materials. So also here for the steel scrap in the truck delivering the steel scrap to the steel plant, we have developed a different setup. Here we have the nutrient generator again mounted on a gantry to scan the scrap surface on the truck of a truck loading at the entrance of the scrapyard. So now we have analyzed the metal scrap by means of statistical methods and by means of sensors. Now we have characterized the properties of the steel scrap, and now we have to optimize the charge mix for a certain metal melt to be produced. And so based on this information on chemical composition and metallic yield, a scrap mix optimization software was developed to determine the cost and quality optimal scrap mix for production of a certain metal alloy quality. So you can enter the quality characteristics of the metal melt which shall be produced, and this scrap mix optimizer will then calculate the optimal scrap mix which has to be charged to the furnace to achieve the quality of the metal melt. And this is done especially for the steel scrap by means of such an optimization system. For aluminum making, the main task of this optimization tool is to determine the amounts of further scraps and alloy materials to be added after an analysis of a sample taken after meltdown of the first charge of chips and aluminum scrap material is available. This can be seen in this upper part of the slide. So coming to the lead production, these two components, the characterization of the scrap material and the optimization of the charge mix have been combined in a smart visualization tool where you can characterize the scrap materials, then in the furnace charging module, the optimal selection of the raw materials and also the fluxes to be charged to the furnace for lead production are calculated, and also the costs of the raw materials per each cast are determined. And in this application, also a temperature control module monitors the melting process to detect failures occurring in the different stages of the melting process. And this tool is also serving as a decision support tool to establish set points for oxygen and gas injection. So regarding the liquid steel production, we have developed a complete dynamic process model for the electric arc furnace, which is used to melt down the steel scrap. So in this sense, the profiles for the energy input have to be adapted to the actually charged scrap mix, and then a dynamic process model allows for online monitoring and prediction of the actual process behavior. This is displayed to the operator, as you can see here in the upper right part, and the accuracy of such a model is quite good. So we can predict the achieved melt temperature and also the achieved phosphorus content, for example, of the steel melt. And then control actions, including endpoint control, are applied to effectively achieve the process targets. And this is determined by a model predictive control approach. Yes, this brings me to the last slide of my presentation. I would conclude with the expected benefits for the process industry and the transferability of the results. So first of all, benefits, the statistical models and the inline measurement techniques for scrap characterization in combination with a charge mix optimization tool allow to enhance the utilization of metal scrap as secondary raw material. So this means that also low quality scrap types can be used if the application of these scrap types is performed under a very tight control, so that you know exactly what comes into the steel melt, into the metal melt when charging these low quality scrap types. And this in turn drastically reduces the CO2 emissions, which are normally connected with the reduction of primary raw materials like iron or aluminum oxide. So when using secondary raw materials, you do not need so much of the primary raw materials, and this will reduce CO2 emissions drastically. So secondly, the online implementation of dynamic process models allow an accurate monitoring of the melting process behavior. And when embedding these models in a model predictive control, the model can also provide useful advices to the operator to adjust the relevant set points for an energy and resource efficient process control. So as I said in the beginning, we have focused in our project on the steel making, on aluminum production and lead production. But of course, we can transfer the developed tools and sensors also to other processes in the process industry. So we believe that the statistical methods for charge mix characterization and optimization can be transferred to all other process industries where a mix of different secondary raw materials is used. This applies, for example, for the copper industry also, but also for the glass production, where you have different kinds of recycled glass material to be introduced into the melting furnace. And the inline sensors which have been developed can be used also for other raw materials like other metals or also minerals, like they can be used in the cement industry, for example. And the application of dynamic process models makes sense for monitoring of all high temperature processes with a complex energy and mass balance, as for example, melting of other metals or also for melting of glass. Yes, this is what I wanted to tell you about the REVamp project. And if you want to know more about our project, we are performing a hybrid workshop on the 19th of October this year, where we will present the achieved results in more detail. And you can register for this free workshop by using this online application. And you can find all this information also on our project website, the revamp-project.eu. Thank you very much for your attention.
Thank you very much, Bernd. I don't know if they have any questions. I don't see any in the chat, but if you have any, it's the moment to input them in the chat box. Else we will move on to the next project, which is RETROFEED, and will be presented by Roberto Aravello-Turnes and Luca Ferrari. So Roberto, the floor is yours. Thank you.
Hello, good morning, everyone. Thank you, Claire. So I'm going to first make a brief presentation of the whole project, and then Luca Ferrari will talk about the decision support system. I'm going to try to share my screen. Okay. Okay. So our project, the full name is the Implementation of a Smart Retrofitting Framework in the Process Industry towards its operation with variable, bio-based, and circular feedstock. My role within the project is the technical coordinator of the activities, and I work by CIRCE, which is the coordinator center. So we are an industrial project, I think quite big, with 18 partners. We have 6 industries, 6 demos in 5 sectors, and a total of 18 partners with research and technology centers. And we have been working already for almost 48 months. So we are approaching the finish of the project. Our objective is to enable the use of an increasingly variable, bio-based, and circular feedstock in the process industries. And we aim to do this by retrofitting core equipment and by the implementation of advanced monitoring and control systems, and also providing support to plant operators by means of a DSS, Decision Support System, which covers the whole production chain. This approach is going to be implemented and demonstrated in 5 sectors: the agrochemical sector, aluminium, cement, ceramic, and steel. These are the goals we have set ourselves to achieve, which is an increase of 22% in resource efficiency, 19% in energy efficiency, and also we aim at reducing costs and, of course, reducing CO2 emissions. Here you can see a pictorial representation of the concept of retrofit. In the picture, you can see in the center the core equipment, which can be very different things given the variety of industries we work with. It can be a furnace or a chemical reactor. This core equipment is going to be retrofitted in each demo and is also being modeled by a digital twin in each demo. And upwards, you can see there are some processes of conditioning, pretreatment, etc., that are also going to be modeled by a variety of tools, including machine learning. And downwards, the core equipment, you can see the finishing processes that can be cooling or cutting, variety of processes also that are also being modeled by several tools. All these modeling tools, the digital twins, machine learning, etc., are going to be included in the DSS tool, which is composed also by many other tools. For example, tools to calculate KRI, CAPEX, scheduling production, forecasting prices, etc. Our solutions aim at a TRL of 7, so it's quite high. And in some cases, they are already in place and giving good results. So in the aluminum sector, we are working with ASAS. The goal of ASAS is to increase 50% the amount of scrap, to reduce energy consumption, implement a more efficient combustion, and reduce GHG emissions. So to this end, you can see we have developed within the project a new burner, which was first tested in CFD simulations, and there is also a new oxygen injector, also simulated previously in CFD to choose the best design. And here are the final burner and the final injection system, oxygen injection system developed. This is the retrofitting process. This is the furnace and the aluminum furnace. Here are the old burners, and here is one of the new burners in place. And here, this is a completely new equipment, is the lacquering system, which is used to remove lacquers and paintings and so on from aluminum, for example, from the Coke cans and so on. That allows to use all these new scrap to be included in the project. And this is the result of all this work. Here we have the scrap that is being loaded into the lacquering system and then to the furnace. And here you can see the final result, which is our very own aluminum billet produced with more efficient. In the steel sector, we have two companies, the Pitini Group and the Antenaris Silcotab. They both aim at the same goals, which is the reduction of GHG emission, use of alternative feedstock, and to improve the monitoring and control. Here also we have run CFD simulations to retrofit the burners that are used in the electric arc furnace. This one. Here is the final design in concept. This also implements an oxygen lens to increase the temperature of the combustion, and in this way to reduce the amount of natural gas that you need to use. And here is the electric arc furnace. And we have 3 images showing the flame using only the alternative material. This is the flame using natural gas and oxygen, and this is the flame using alternative material and natural gas, but with a reduced amount of natural gas, so you can see that the flame is quite powerful. In the steel sector, we are doing tests with several materials to be the providers of carbon. We are testing polymers, tire grains, limestone and enriched polymers, and also biochar. As you can see here, we are doing extensive tests with a lot of material and trying them in a lot of heats of the furnace. And these are the trials with tire grains. Here, what we are achieving is a high substitution rate with tire grains, so a new alternative material. And the goal of this test is to reduce the global anthracite consumption. This is for the 2 demos in the metal sector, and I'm going to give a brief overview of the other demos just to complete the overview of the project. In Fertiberia is in the agrochemical sector, and they are aiming to replace the 10% of the currently used phosphorus sources. This is going to be done with a new reactor that was first tested in CFD simulations and then was commissioned to an engineering company. And this is the result, the new reactor that will be placed in the next few weeks. In the cement sector, we work in Portugal with Sept. They are aiming to replace 100% of the fossil fuel by alternative sources, in particular RDF. This allows them to reduce CO2 emissions, increment energy efficiency, and they are also installing new novel sensors. Here we see the new burner that was tested in CFD simulations, and these are the array of novel sensors that are going to be implemented, which are image-based sensors here, and also sensors to measure the quality of the clinker. In the ceramic sector, we work with Torretit in Spain. They are aiming at reduce the waste material, reduce natural gas consumption, and improve their monitoring and control system. We have developed a digital twin of the furnace that you can see here, the real furnace. This is the heat recovery system that is allowing to reduce natural gas consumption. And we are also implementing some other models to, for example, to model the cooling of the final product. That is allowing to reduce the consumption of water, for example. And here there is the novel sensor that is also an image-based sensor that allows to control the amount of raw material inside the furnace, and that way to reduce the amount of waste. And here we have the real impacts that we have achieved in ASAS, the aluminum demonstrator. You can see that we have excellent marks. In resource efficiency, we aimed at 48%. We have reached 57%. In greenhouse gas emissions, we have reached 75% reduction. We have reduced fossil fuel resources almost 20%, and energy efficiency has improved almost 20% also. And these are only the first trials, so we are confident that we can improve this in the following weeks when everything comes into place. And this concludes my overview of our project. I would like to conclude inviting you to keep tuned for our final event, will be 25th of October. And we would be pleased to see you there to share our final presentations. And now I'm going to leave the floor to Luca Ferrari, which is senior consultant in Optit, the partner who is developing the DSS, our decision support system. Thank you very much.
Okay, thank you, Roberto. I hope you can hear me. So let me share my screen. So here, you should see my screen now. So I'm Luca Ferrari. So as Roberto said, I'm a senior consultant in Optit. So let me swap I think I have the wrong screen.
No, it's okay. We can see your presentation.
Okay, in the presentation mode or the?
No, it's not presentation mode, but it's okay again.
Okay, but I can change it. You should have too many screens. Pick the wrong one. Sorry about that. Just give me 1 second. And okay, now you should see the presentation, right?
Yes, perfect.
So basically, what we build in Optit, as Optit, we are a company specialized in the development of digital tools that leverages upon artificial intelligence and operation research algorithms. So within RETROFEED, what we built was a decision support system that could orchestrate a series of models, as Roberto explained before, to optimize and simulate the various industrial processes. So what is a decision support system? Just briefly explaining to you. It's a tool that could support operators and decision maker within any industry in taking more informed decision based on the data that you have available. So it could be strategic decision regarding retrofitting or investment, could be long-term type of decision, for instance, budgeting or planning yearly production, or short-term, weekly or monthly production plan is one of the most commonly used case for supporting decision, or operational decision. So daily operation, it could be helped by having a tool that could be used to take informed decision, and I will show you later an example. So how is the DSS integrated within an IT stack? So we know that most of the data will come from sensor and actuators, the PLCs and the SCADA, which are the backbone of the current industrial IT information stack. What a lot of companies are building now, we are in the phase where a lot of companies are investing in MES system and other type of tool to start using the data that are collected in a more appropriate way. So what we try to build here with the DSS is something that could get along with the MES or other type of tool, replace in some instance Excel or other type of business intelligence application to run what we call descriptive and prescriptive type of analytics. So we have analytics app that could be used to analyze and monitor the data, optimization app that could help in taking decision, and simulation app that could be used to basically evaluate beforehand how the process would behave, considering different parameters. As Roberto explained before, what we did in all demo cases, we built a digital twin, which is the core of the application. Could be built with, we use different type of languages. And around the digital twin, we build what we call value chain models. So a model that could optimize the injection of raw materials or the use of energy for that specific process, and at the same time monitor the emission and the process output, considering very important what is the cost of that type of production, not only the energy involved. But let me show you quickly. I will change my screen and I will show you quickly the application. So here we have maybe I have the wrong screen again. Sorry, Teams is behaving a little bit weird. I need a bigger screen. So let me show the application quickly. So here we have the main dashboard where you can see a simulation of a production batch. So on the top left, you see a list of tests that we've done on a specific process. In this case, it's the steel process, where we try to simulate one single batch of production. And here you can see a different test where the digital twin simulated the process. On the bottom, you have a table with a series of KPI, which summarizes the the batch production, you can change the view. You can evaluate different type of KPIs. So for instance, it's very important to see the cost of that type of production. And on the right, you see the same KPI, but on a timely base. So here you can see, for instance, these are just examples of KPI, but you have electricity consumption on a minute base for gas and electricity. You can change the view as well here. So you can have an understanding of what the future batch could look like based on the input that you give to the model. And the input, you can change them. You can put different type of information. You give a name, you provide the quantity that you want to try, and you put a name. And here you can really go into the detail of each simulation. So you can decide that maybe you have raw material, you don't have that raw material available, so you put that to 0, and that the model will take that into account. So it will not use that type of material. And based basically on one of those value chain model that we build. I'm not going to run it right now because it takes a few seconds and it's not good for the presentation. But here you basically, the model takes into account all the different parameters correlated to the various raw material and will simulate the process. Here you can input other type of information, for instance, cost and prices of every information that you have for the model, so the cost of electricity, the cost of gas. So you can really simulate, for instance, you want to try something where the cost of gas is way higher, like considering what happened last year, you can change that. You can run a quality model that could be used to pre-evaluate based on the input, what's the expected outcome of the system. And then you click run, and the model will simulate and return this type of result. You can compare different test product, and then you can see in different chart what are the main difference between the two instances. So you can make different simulation and see how the model behaves. The last dashboard I want to show you today is the test production, where you can really simulate, for instance, the next 24 hours of production. So here I launched 3 different batches, and you can see here on the chart, similar to what was done before, you can implement different type of parameters for the various part, and see them on a chart where you see basically 2.5 hours of production in this case, and on the bottom the summary of the 3 batches. So you have product 1, 2, and 3. And here you have the energy component and the input, or you can evaluate the cost. Everything here can be connected to real data. So in case you want to connect the actual plant, you can even see the measured data, and the framework that we build will calculate all the KPIs based on the measured data from the factory. And then you can make comparison between what's the simulation would look like and what the actual production was. So in this case, it can be used also as a sort of a forecasting type of application where you run the simulation for the next 24 hours, and then you check what are the discrepancies between them. So this is what we build. Is basically a framework that could be used in multiple processes, depending on the type of model that you want to connect and the type of data available. So I will go back to the presentation, and here at what stage we are right now. So we are almost at the end of the retrofit project, but we built the tool in such a way that could be leveraged in the market. So different models, if they were available, could be connected to the system and could be used within the framework. So we are looking at the moment for, we are trying to replicate the study in other type of furnaces within the retrofit demo cases, because we saw that there are a lot of advantages in using digital tool to understand production. But we are also trying to leverage upon this experience to build a tool that could be used by the entire industry and definitely improve the current situation, considering the target that the EU will settle for environment and so on. So thank you everyone for listening. and I give the floor back to Claire. So remember to enroll, as Roberto said, to our final event in Brussels at the end of October.
Yes, thank you very much, Luca and Roberto, for the presentation of RETROFEED project. If there are any questions, I don't see any in the chat at the moment. Just to give you a minute if you have a question, else I will ask Eric van Dijk from the Initiate project to start his presentation. This is the last project on the agenda, and then we will move to the panel discussion. So I see no questions. So Eric, the floor is yours. Thank you.
Okay, thank you very much, Claire. So let me share my my screen. This should be visible for all of you.
Yes, perfect.
Correct? Okay, good. So I will be presenting the Initiate project, and in contrast to the previous two projects, REVamp and RETROFEED, which are closing the end of their projects. So plenty of results indeed have been presented. The Initiate project is about halfway through, so I will basically give you an update on the project, the status. So my name is Eric van Dijk, indeed, project coordinator, and I'm working at the TNO in the Netherlands, the research institute. So to start with the concept and the vision of the Initiate project, the Initiate project is really about the demonstration of one symbiosis system between the iron and steel sector and the ammonia and urea production. So linking two main industrial processes which are very carbon intensive, aiming at using the off gases from the one process as a feedstock for the other one. And what the vision of the project is that we want to create a bankable case for the first commercial size demonstrator, actually producing 50 kilotons urea on the basis of BOF gas. And the project will take all the steps necessary to develop this first of a kind plant. And very importantly, in that is the demonstration of the process, so the continuous production of ammonia from BOF gas at a significant scale. But also, of course, for the business case and the rollout, the site identification and the business plan development, and the IP and our ownership and collaboration models are going to be developed within this project. So first, some words on the concept itself. Here we see block diagrams on the left-hand side of a steel plant, really very simplified, but it gives the most important processes. And on the right-hand side, the production of urea. So to start with the steel plant, you have iron ore intake, coal intake for traditional way of steel making, coke plant producing coke oven gas, blast furnace to make pig iron, and then basic oxygen furnace to make steel, and then you do the casting and rolling. Well, the coke plant, the blast furnace, and the basic oxygen furnace produce off gases which have caloric value, and they are normally used internally, and the surplus is used in the power plant to make electricity, which also goes back to the steel plant for the most part. For urea production, it's normally done by reforming of natural gas, cleanup and CO2 removal. Then you produce from the hydrogen-nitrogen mixture ammonia and recombine that with some CO2 to form urea. Well, as said, both industries have a significant carbon intensity, typically for both close to 2 tons of CO2 per ton of product. So being hot rolled coil for steel or ammonia for the ammonia industry. And both industries are also looking into ways of greening up. So for the steel industry, there's a trend from switching from coal as a reductant to natural gas and hydrogen. CO2 capture is an option, as was also presented by Sept, of course. More increase the use of scrap is a good way, as was illustrated by REVamp, and of course efficiency. So these online modeling tools that are presented in the previous projects really help in this respect. For the ammonia sector, they are considering, of course, CO2 capture and also the use of green hydrogen. And what we are developing is actually demonstrate the symbiosis between these industries. So how does that work? We are going to take the BOF gas, the basic oxygen furnace gas, and use that as a feedstock for the ammonia and urea production. And why the basic oxygen furnace gas? That's because this product has a very favorable nitrogen carbon monoxide content. So if you would apply water gas shift to that, so convert the CO with steam into CO2 and hydrogen, remove the CO2, then with the resulting product, you have a very nice ratio of these two gases, these two reactants to produce ammonia. And then with part of the CO2, you can combine it to form urea. So you have CO2 for sequestration, and you have a certain amount of CO2 that you utilize to make urea. So this is the concept that we are going to demonstrate and going to build a business case for. It has two enabling technologies, which is the sorption water gas shift technology by TNO, and a novel type of ammonia production loop by NextChem and Stami Kabel. So these are an overview of the partners in the project. We are 11 partners. It's a 5-year project. As said, we are approximately halfway now. 21 million euro subsidy project, and half of that is approximately allocated to the demonstration of the technology, so building a pilot and operating the pilot. We cover the whole value chain from material suppliers and equipment suppliers, Johnson Matthey, and Kisuma for the materials, the active materials, TNO NextChem for the technologies, so the equipment, and it's going to be demonstrated at Sweden in the northern part of Sweden. And we have technology licensors, Stami Kabel, NextChem for the ammonia loop, and TNO for the sorption water gas shift technology. And we have end users, the big steel industries in Europe, SSAB and ArcelorMittal. And we have knowledge support from universities and CO2 Value Europe. So that covers the whole value chain. So some words on the enabling technologies. As mentioned, there's two of them. There's the sorption water gas shift technology, which is developed by TNO and is a solid-based technology for efficiently removing CO2 from a feed gas and simultaneously performing the water gas shift reaction. So with the BOF gas, we aim for a hydrogen-nitrogen rich mixture in the top for ammonia production and CO2 for storage. And the second one, as mentioned, the ammonia loop developed by NextChem. This particular loop is suitable for variable hydrogen-nitrogen ratios. And why that is, I'll explain in a minute. And it has a simplified knockout and recycle loop in the ammonia section, and we think it's very suitable for dealing with dynamics which are inherent to the feed. This is the PER diagram of the project. We'll not go into detail, but it's clear from this project, from this diagram, that the demonstration is an important aspect of the project, and then the modeling for understanding the layout of this concept, but also the commercial implementation plan. So I will give you an update on both the demonstration and where we are with the modeling. So some pictures for the we are currently building the pilot, or actually we are reusing a previous pilot. And these are some pictures of hardware that is currently being constructed and installed. Very nice to indicate that in 2017 we have installed a single column CWAX reactor, so sorption water gas shift reactor, And that has served for 6 years in different projects, and we have now removed it, and we will build a 3-column system now to demonstrate the whole cycle. Here you see on the right-hand side the modification of the foundation for positioning of these 3 reactors, and these are actually the 3 reactor tubes that are going to be transformed into reactors. And here is a design of the ammonia loop reactor, 350 bar novel ammonia loop reactor that's currently under construction. So a lot of things are going on for the pilot, and we aim at executing our first campaign actually at this time next year, approximately. So that's work ongoing. So some words on the modeling. It's a significant part of the project. First of all, the dynamic modeling of the process. And that's really important in the sense that we take the BOF gas, and the BOF process itself is a batch-wise process, so it's inherently dynamic, and we have to deal with these dynamics in converting the feed gas into ammonia. So typically in a BOF cradle, you have these blows, and only during the blow you collect the gas. So that needs to be stored in a buffer vessel. And most of the times there's multiple of these BOF cradles working in parallel. So that will create a continuous product flow, but with varying composition, as is illustrated here. You see that it's quite dynamic in the contents of CO and nitrogen and CO2. And well, we have to design a process that can actually handle this. So understanding these dynamics, modeling these dynamics, and optimizing the downstream system for this is a really important step in the process. For that, indeed, we also create a dynamic twin of the process. So currently we have dynamic models of the feed section, the water gas shift, our absorption and water gas shift, buffering, and the cleanup of the gas, and we are currently also working on a dynamic model of the ammonia loop. So in the end of the year, this whole process will be described by dynamic models, and that's used then for the pilot, of course, but also predictions on real scale plant behavior. Okay. The other modeling is, of course, on techno-economics, life cycle analysis, and the business case aimed at the quantitative analysis for direct comparison of different options. So we have defined base cases, reference cases, and those will be compared, or the initiate case will be compared against those two. And of course, we will include scenarios for the evaluation of CO2 intensity of electricity, for example, fuel mix as a general characteristic, and also pricing of different feedstocks and products. And of course, for the business case modeling, location-dependent assumptions are really critical. So this work is really ongoing now, and we are considering the steel plant, of course, at a 3 million ton hot rolled coal per year capacity, and we are considering 2 sizes of ammonia and also urea production. And the sizes we consider are linked to what kind of gas that we want to use. So for the small size, we will only take the BOF gas from the steel plant and use that as input for the ammonia production. But we are also considering that additionally we can use the blast furnace gas. Well, and the blast furnace gas has a much higher nitrogen content, so that needs either nitrogen removal or hydrogen addition. So this is a little bit more challenging compared to this, but it's good to have, of course, the projection for both routes. So the base cases are the individual processes, so steel on the left-hand side and ammonia on the right-hand side. If you then look at the reference cases, so reference cases means the individual processes, but then decarbonizing with existing, more or less existing technology. So for the steel, that would be send all the gases that go to the power plant to a decarbonization unit. So water gas shift and amine scrubbing. So that's the reference case for the steel plant, and the reference case for the ammonia is to send the flue gases from the reforming section via ammonia scrubbing to decarbonize the flue gases there. So that's the reference cases. And then the initiate case, as presented before, use the BOF gas for small scale at least, use the BOF gas as input for the ammonia production. And to give you an indication of the potential of this technology, these are some, I should say, preliminary results on the techno-economic modeling. On the top, you see the small scale implementation. So we only use the BOF gas to make ammonia. So that's a relatively small sized ammonia plant. The dashed lines are for the reference technology. So steel and ammonia with the CCS. And the solid lines are for the initiate industrial symbiosis case. And what is presented here is the cost of carbon avoided. And you see that over a wide range of natural gas prices and electricity prices, the initiate case outperforms the reference cases. This is also true for the larger scale. So taking both the BOF gas and the blast furnace gas to make ammonia and urea. However, the difference is smaller, and that's mainly because you need to compensate the high nitrogen content of nitrogen with, for example, hydrogen from electrolyzers. So that's a much more energy intensive system. And it also means that if you take out both of these gases from a steel plant, they have to supplement the energy content for that. So that also requires additional natural gas or electricity. So this is a much more challenging case, but at certain pricing, you see that we can outperform the reference cases. So that's a first indication that this symbiosis symbiotic concept makes sense, and we are definitely going to detail that further on in the project, of course. So to end my presentation, I want to give you an overview where we really aim at the beyond demonstration application after this project. So we do the value engineering and the integration to reduce costs of this concept. This is actually a kind of pre-feed study to get to a bankable first of a kind plant at a selected location. So that's all part of the project to sort that out. We heavily going to rely on artificial intelligence for the control of the BOF gas dynamics, because we consider that as one of the challenges for this project. And we will quantify the social, economic, and environmental impact of this particular industrial symbiosis system to be rolled out principally in Europe. And with that, I would like to end my presentation, and if you have any questions, feel free to ask.
Thank you very much, Eric. Yes, I see we have one question. If you can type it in the chat, please, the person who raised their hand. I see earlier I overlooked a question also for Bernd. So first we take the question for you, Eric, and then we come back to the question to Bernd.
Yeah, sure.
No, please type your question. Okay, so let's start with the one aimed at Bernd. The question was, can you elaborate on how impurities in the scrap are removed?
Okay, so actually this was not in the scope of our project, but Of course, when you use especially the lips sensor to detect, for example, particles with higher tramp element content on the conveyor belt, you can also use this information to control a robot to pick up these scrap pieces and to remove it from the scrap stream. So this could be a possibility. Also, the same can be done also with modern camera systems, which allow to detect scrap pieces with a higher tramp element content, especially copper, but also non-ferrous, non-metallic parts like plastics or organic material. And also this information could be used to control a robot to pick up these scrap pieces and remove them from the stream charged into the furnace. Does this answer the question?
Yes, we have another question. So 2 questions for Eric now. How much CO2 can be removed from BOFG usage in the project, since it's the highest emitter of CO2? And the other question is, do you need to remove additional impurities and gas cleaning between BF gas under your production?
Okay, thank you for these questions. To start with the first one, so if we take in both gas, we now do the system analysis for taking all the both gas, so there's none left for the steel plant itself. And then we are aiming at a 95% carbon capture on that stream. 95% meaning you have to remove all the CO2 for ammonia production, but 95% of that removed CO2 is then ready for storage. That's a different if we look at the system where we both take in blast furnace gas and BOF gas, so that we also aim at these kind of avoidance ratios, but we should keep in mind that if you take away blast furnace gas and BOF gas from the steel plant, that the steel plant still needs to have energy. So that needs to be restituted by something else, and what you are going to use for that really determines then the total CO2 emissions in that case. So that's a much more complicated picture there. And the second question was on impurities, how much impurities we need to remove. We have made a quite extensive study on the impurities which can be found in both gas and in blast furnace gas. We are analyzing what the effect is on the different process steps that we take. The water gas shift section and the sorption enhanced water gas shift section are quite forgiving considering impurities, and also already transform quite some impurities into less harmful components and simultaneously remove them. We still need indeed sulfur cleanup after we have produced a hydrogen-nitrogen mixture. So that will still be required. And I hope that answers that question.
And you have one more question, which is how much reduction of CO2 can happen per ton of crude steel in case of BFOG?
I don't have the numbers. I don't know the numbers from the top of my head, but basically we recover more about 90% of the CO2 that is in BOF gas, and BOF gas I think is 10% of the total gases that are produced in a steel mill. So yeah, in that order of magnitude.
All right, thank you. I see no more questions, so we will move to the second part of the third part actually of our event, which is the panel discussion on replicability. It will be moderated by Dusan Yakovlevich from EIP, our policy director, and we have 3 panelists: Tutku Odzon from Assas, Marianne Flores-Granobles from ArcelorMittal, and Diana Mayer from Sydenor Innovation and Development. So, Dusan, the floor is yours. Thank you.
Thank you, Claire. Thank you so much. I hope everybody can hear me. I mean, you know, looking at the title of the event, you know, it's kind of interesting. I mean, we start kind of the upside down. You know, we covered really well, you know, the second part of the title about showcasing and retrofitting and circularity. But what I would like for this short time, you know, if we can, you know, speak a little bit about kind of how we can use all of these things to transform the metal industries. And the 3 panelists, you know, they're basically from the companies. So these are the perfect people, you know, that can reflect on what has been discussed. You know, I mean, at EIP, we work quite a lot on replication and replicability strategies in the business. But, you know, our kind of expertise is not really like, you know, the technical replication, but more sort of market orientated and contextual kind of replication of it. So opportunity now is, you know, I would like, you know, 3 panelists to briefly present themselves, present their related work, and possibly, if they can, you know, kind of reflect on something that they heard in the previous presentations, on which we can kind of build up, you know, some discussion when it comes, you know, to sort of to market orientation, what we just listened about. So, Tutku, your camera is off. You know, you're first on, but maybe we can start with Diana.
Good morning, everyone. This is Diana Mier from Sydenor. I work for Sydenor, which is a special steel maker located in the north of Spain. My contribution to the REVamp project, together with the Dr. Claim, has been on the dynamic process modelers, applied both to the scrap mix optimizer and also for dynamically assessment of the electrical furnace.
Thank you. Thank you. Tutku?
Yeah.
Tell us a little bit about yourself and then basically kind of what you do and also, you know, like reflect, you know, on some of the previous presentations.
Yeah, this is Tutku Özan from Asaş Aluminium. I'm contributing to the RETROFEED project. I'm a metallurgical engineer as a job here, and I contributed to the RETROFEED project to retrofitting of the aluminum melting furnaces in order to decrease the carbon dioxide emission and integrating the lacquering drum system to enable alternative feedstocks to the production cycle. This is our role in the project.
Thank you. Thank you. Marianne?
Yes, hello everyone. I'm Marianne Flores. I work for ArcelorMittal. I'm located in Ghent, Belgium, and we are part of the Initiate project, which was the one that Eric just introduced. My background is actually in chemical engineering, so you may wonder, what is this chemical engineer doing in steel making? Well, we have the problematic of the CO2. And when we enter on the part of how can we improve the process upstream to minimize our CO2 emissions, or which type of technologies can we include in the supply chain to help with this, yeah, then it's very important to have this background. In my role now, I do more like technological assessment and economic assessment of potential technologies. We emit a lot of CO2. We operate in more than 17 countries. So maybe some solutions that could work in Europe will not work in other countries. So yeah, it's all regional dependent. Yeah, so I'm happy to be here.
Okay, thank you. I mean, we had the presentations in the first part of the program were sort of quite technical, and all 3 of you have kind of quite good technical knowledge, it seems to me. So I kind of work, looking at I mean, all three projects, actually, they spoke about the business models, and they spoke about replication, and they spoke about potentials, what can be brought, how can this be brought to the market. So now, if you're sort of thinking from, not as your own company, but like some company that actually has not heard of this technology and the innovation that you work. I mean, what would you think that would be kind of the selling points? What could be something that can be like, help this technology specifically you're working on, to be kind of like, the present on circular industries market? Diana, please, first.
Yes, thank you, Lisan. So for us, I would say that the transferability relies perfectly with the, for example, retrofitting solutions based on the advanced monitoring systems. Within the REVamp project, we have further developed, as perfectly was explained by Dr. Klein, the LEAP system and the neutrons sensor generators. These such systems are very accurate for providing, for example, the characterization of the chemistry of the scrap. So among the metal making industries, obviously it's totally transferable, but also it could be, for example, other technologies that are also of interest and developed under the frame of the project, like, for example, all the retrofitting solutions based on simulation and optimization of the processes. We are, as very well explained by Marian, a very CO2 emitters. So we always are looking forward to the sustainability of our plants. So these kind of systems that are of great importance for those footprint impacts can be very well addressed. No? This can, for example, within the REVamp, the online assessment of the status of an electrical arc furnace not only gives an input in the CO2 emissions, but also in the transferability to other companies to let the status, the knowledge of the status. Okay. And it's totally transferable also to other melting processes and companies.
Tutku, the same question, basically, kind of transferability and replicability of your solutions into the market.
Yeah, from an profit concerning industry point of view, the main challenge, main aim for an industry is to sell something. We have integrated these solutions in pandemic time, and where we have get too much requests from our customers, and it is very challenging for us to integrate this kind of solutions. Also, in the first time in history in Asash, we have bought external aluminum billets due to these integration studies. So this is a little bit hard to retrofitting solutions or using alternative raw material solutions, a little bit hard in the first scale, but I suggest other industries and to whom wants to increase the circularity first, that they can more get the point from the digitalization studies. For example, decision support system.
You frozen. We might have lost you. Marian,
Yeah.
Do you think you can? Okay.
Yeah, well, Tutku comes back.
Then she comes back in a minute. But she actually raised one point, which I'll come back to later. But please, the same question.
Yeah. So if we see it, for example, when you do innovation within the steel plants, let's say you can develop a technology and then you have certain challenges like Diana discussed for the implementation internally. But for example, when we talk about circularity, it normally involves other parties that then add an additional challenge that is not only the technical one, but also the geographical location, for example. So if you want to implement, for example, a CCU project like the one that Eric Tuktu just came back. Yeah.
Please finish,
continue? So, for example, the one that Eric just discussed, we are talking about the steel plant where we will use the basic oxygen furnace gas to make a chemical. It doesn't have to be only ammonia and urea. It could be also another chemical. For example, there was a project that we participated about 4 years ago where we were using the carbon to make polyols that then will replace fossil polyols to make polyurethane. But to replicate this, you need to have a chemical plant that is close to the steel plant. Otherwise, you will need a big investment on pipelines or transporting either the gases or liquids. So that's something that creates some challenges for the replication.
Thank you. Tutku, we have you back. Do you want to?
Yeah, I'm sorry. I lost my connection on my computer, so I have connected via my phone. Sorry about it. So to summarize what I have told before, it is very hard for industries, profit concerning industries, to implement such a solutions because we should make a cut in the production line, make a break for production line. So I suggest to first implement the digitalization solutions. For example, decision support system. It very satisfies operators and the engineers on the cast house, and it allows us to make trials first on the digital environment and then make the real-time trials. So thus, this kind of solutions, for example, digital twin or decision support system, very contributes to companies who tries to increase the circularity effect.
No, this is brilliant. I mean, I do have a following question, but I would like to invite the participants to join and to post any questions in the chat, so the question and answers section. Tutku, I mean, before we lost you, and importantly, you came back to it actually right now, is that I mean, the industries are profit-oriented industries. They do what they do. They're not really like looking at how to increase circularity in their sector or elsewhere. And you also mentioned digitalization, and I know like we had a presentation from Luca from Optit, which is interesting. It comes out as sort of technology enabler, somebody who can kind of make things visualize the changes in the company and then the support and help decision-making processes, which is usually important for external potential places where our technologies can be replicated. My question is that, I mean, all of these solutions from the projects, they have kind of high potential for transferability and replicability. But my question is, who's going to do it? I mean, you as a company, your company, you're not going to go around, and basically talk to competitors or even, friends or different sectors, God forbid, and trying to make them, follow what you do. But who can bring this to the market? Who can be the actor or the system, or how can it be done?
In my opinion,
Tutku, yeah.
In my opinion, companies who try to swim in the blue ocean needs to make these kind of improvements in their facilities. For example, in aluminum industry, we are commonly working with automotive industry, and they have new regulations. For example, if we don't act right now, we won't be able to sell any materials after 5 years from now. So also, European Green Deal is such an important thing in here too. We need to consider this once. The Earth don't have enough raw material to produce primary production in here. So we need to circularly evaluate this kind of materials from the scrap. In this retrofit project, we both able to decrease the carbon dioxide emission and total carbon equivalent in the aluminum billet production, and also we have able to use alternative feedstocks. So this project serves for all, and all of the production companies, metal sector needs to do something about it, even with their willing or with the force of the nature and the other companies.
So you think it should be more kind of regulatory incentives. Marian, I mean, the same question basically. I mean, who can be the agents to bring, what you're doing to the market, or who or what? Could it be like, the third-party companies, could be people like Optit, or some technology consultancies who have interest to developing business, or as Tutku says, initiative should come from the regulation?
Yeah, I could talk a lot about this, but I'm gonna try to be short just because of time. But let's say that if we see the business as pure business, the idea is to sell a product, and then you need to have a market that should buy these products that you are making. We see from the regulation point of view, the government has this ETS taxing system for the CO2 emissions. And I speak a lot about CO2 because we overall make 2 tons of CO2 per ton of steel that we make. So it's a lot. And this will gradually increase over time if we will not do anything now. Basically, the cost of the steel that we will produce in Europe will increase a lot, and we will lose market competitiveness with other continents. So if we want to be competitive and we want to remain playing in the market, we need to invent something to try to reduce this. So then, okay, it could be an investment that we know that if we invest this amount of money, then we will be able to save this amount of CO2 that at the end are taxes that I will not pay anymore. So let's say that that's kind of an incentive, but then how is it executed? Then it depends on the company itself. So if they have an R&D, then they might develop technologies internally. But if the company is smaller, then they depend on the technology providers that they will come. And then basically it will all depend on the business case. There are technologies that are very electricity intensive. So then the costs are mainly driven by the price of electricity. And some of these technologies are not economically viable just because of this. So let's say there can be many options over the table, but then at the end, the go decision will depend if there is a feasibility for this.
Okay, so it's almost kind of like, Tutku says, like a regulation from the top. You said it's almost kind of survival game, to ensure kind of competitiveness for European companies.
Yeah.
Diana, I mean, the same, who can do it or what can do it?
Yes, I would highlight 2 ways. I think that it's very close to the explanation of my colleagues. No? First one is, for example, we work very closely with our technology suppliers and our material providers. No? When you want the circularity and the symbiosis with other close companies, and we want, for example, to bring a product that is our co-product. In fact, we are in a very close relationship with them. And second way is absolutely the open innovation. We are we are developing products like in the REVamp project that have a potential to be in the market. So I think that all research centers, universities, startups are the ones who are pushing up these open innovations. For us, it's of great importance that.
No, I mean, this is super important. And I mean, we've been working in industrial sector, and kind of replication of the good solutions and technologies and products, for decades now. But I mean, open innovation, it comes, in a way, I mean, working from kind of industry and industrial sector, it's all about prices, and it's all about competitiveness, and it's all about jobs, and it's not very sort of naturally open world. I mean, Marian, what do you think? I mean, what does open innovation, does it resonate with you? I mean, could this be one of the ways, that we can kind of, replicate upwards our work?
Yes, I think that also, for example, these opportunities that you have to develop technologies that maybe are at low readiness level, like proof of concepts developed in universities, then you have the opportunity to scale up these technologies using European funding, for example. And then you can put together industry with research centers, universities, and these results, most of them are public. So then you can follow up a project, like, for example, the 3 that were presented here, and you can learn something from that. So I think definitely that's something that helps a lot in this challenge.
Same, Tutku, open innovation. Can we all be friends and just, work all together?
Yeah, I believe so. It must be do something like that. So both universities, institutes, machine developer companies, technology developers, and industrial validators like Asash do should be working together in order to create solutions more efficient. Because if we don't have, for example, the institute, we won't be able to use these kind of solutions in the first time. If we don't have the equipment developer, technology developer companies, thus we won't be able to use this kind of technological solutions. If the consortium don't have us, so they won't be able to validate something. In order to create an efficient solution for future, they all must act together.
I mean, this is also kind of, all what you said, three of you, it kind of resonates through my experience from EIP. You need kind of like third party, you need enablers, and you need really, the people or separate people with sort of industries, because and I said, we all kind of do our work. What about money? Who should pay for European industries? Now we have we have solutions, we have agents to bring these solutions to the market. Who should it be supported in which ways? By market or European Union or private funding or banks? Is it really kind of financially viable? Marianne, what do you think? What do you think about money issues for this?
Yeah, I think when you develop a project, you need to evaluate the cost that it will bring you to build the facility or the technology, and then you have the cost associated to operating that technology. So if you see it from the capital investment point of view, well, from the steel industry, we pay a lot of taxes. So you could think that actually this could be a reinvestment if we can get partly funded these capital investments. It's like if we would have taken this money and just invested ourselves in the technology. But then is the question not only, okay, I build my facility now, but maybe that technology that I'm going to run is going to increase by double the cost of the steel I'm going to produce. Then I know I will not be able to sell this steel. So then you need to discuss with, for example, in the point of view from the electricity, who's going to produce electricity I need, or who's going to provide this alternative feedstock that I could use. And then this will be normally separated plants, because we make steel, we don't make the resources that we need, we just buy from other people. So then they need to enter in the same conversation. Normally it's with the government, because if you want to create a new concept, you also need to have all the approvals of the processing. So I think money-wise, it should be capital with support of the government using this money that we are already paying in taxes, and then in the operational costs, we need to understand what is the market need and which parts do we need to cover to make sure that this energy and feedstock that we need are available at a feasible cost.
Diana, can you say what you think?
I think that when, for example, when it comes to financing innovation, which has an inherent risk of failure, obviously for private companies, to have a financing from the start or from the beginning of a project is very important, because it's, from time to time it happens here, that you want to run a project, but you have uncertainty, you don't know what will be the outcome of the project, and normally there are very successful projects, but there are others that not that much, So I think that when it has an inherent risk of failure, the financing, the public financing is crucial. It's absolutely of major importance. On the other hand, for example, when you are rising on a technology that is quite well proven at the market, and it just has to be partially modified for your ad hoc solution and etc. I think that the private funding is easier, and you can accomplish that. But for us as an R&D department, the financing from the European community and etc., and all the supports with our colleagues from research center and so on are of major interest, because otherwise we could not afford apply research actually.
Thank you. I mean, Tutku, I left you, because, you have this kind of, you're based in Turkey, so you have not just sort of EU-orientated market position, but, this kind of, form of a global view. I mean, I understand all of you are global companies, but, you're coming from there. I mean, what's your perspective? Who should be paying for this?
I believe all public organizations, both municipalities, governments, and EU, all need to, let's say, make some funding or something for this kind of topics. But eventually, even if it's not very profitable at the moment to retrofit something or to integrate circularity solutions into the facility, it will be eventually. So we need to get the action from now.
Yeah.
If not, it will be more costly to produce in this today's technology in after 5 years, for example.
Thank you. But I don't see any questions coming from the audience yet. Hopefully we can have some participation. But just to follow up on this discussion, I mean, what about the customers? I understand, like there is a green steel initiative. I mean, there's sustainable aluminum label initiatives. But from our experience is that the customers, they're not really like ready to purchase things which might have been priced differently on the basis of sustainability of their production, where like the price, is still the main kind of decision-making element. Could there be like not just to build up on the innovation, but also kind of to create more sustainable metals? Could there be like some regulatory form? Because we don't sell to the end consumers. It's also to part of sort of the business supply chains. What kind of incentives can be put on the customers or on your customers, to they look, that these elements that are the metals are produced more sustainably? Tutku, please.
Yeah, as far as I know, the automotive industry have this kind of regulations at the moment, because we are getting some requests from our customers to produce, let's say, green aluminum ingots or billets to be able to sustain lower carbon equivalent degrees in the production area. So some industries don't have at the moment, but they will be in this topic, I think. For example, I know automotive at the moment, but railway sector, aerospace sector will also in this line in the future. Also, architectural sectors and some energy sectors itself, it will be making this kind of regulations. It will be a mandatory thing.
Thank you. Diana?
Absolutely.
Green steel, is there a future for green steel?
Absolutely. I was mentioning that, in fact, the green steel, no? You know that nowadays what we are selling at Sidenor is the green steel, which is a new brand of product, no, for us, which means that when we are supplying billets or blooms, they are coming with a certificate that we are that green, and we are allowing people to know, or our customer to know, what is the footprint that is achieved within the whole chain of the manufacturing process. So this driver that is set by not by the governments and others, but also for our customers, it's very important. And also we are contributing to reinforce our suppliers as well in this sense, no? Because we want to be to manufacture and to sell green steel. And obviously, the renewables materials and renewables energy sources of major importance, but also our suppliers, because if we are thinking in the first chain, no, of our overall process, they are a lot to apport in this sense.
Thank you. Marian?
Well, nothing much to add. I think, yeah, we might might think at first that the decision making is first done at price, but actually internally we do also get requests for green steel. So there is the transition is not going to happen from one day to the next day. I think slowly we are starting to see some movement there.
But do you think that the customers are, Mariana, interested to pay a little bit more, or they don't want to pay more? The prices is basically they still expect.
I think they are willing to pay a bit more, and actually also from the regulation point of view, as Tuktu mentioned, for example, in the maritime sector, by law, they are going to be forced to slowly increase the amount of clean fuels that they use to transport. So there will be a transition just because, yeah, the government is already doing something for the society to understand that it's a change that we need to make. Now we are talking about money because we are seeing it from the industrial point of view, but we also need to remember the main point why we are even talking about reducing CO2 emissions. And it's because we have this climate change and we see things changing with respect to other years. So there should also be kind of a social transition for the society to understand what is the main motivation why we are even doing this.
Oh, thank you so much. I mean, this is in a way, I mean, I see we have basically 2 minutes, but it's in a way kind of perfect way to close our discussion even without participation, because I mean, we started from the innovation. We spoke about the agents of bringing these innovations to the market. We spoke about the financing. We spoke about consumers, and now, you know, you're mentioning society. So it's kind of in a way, it's sort of full circle of this sort of transforming the metal making industry. I mean, it's, you know, we don't work and exist in the vacuum. It needs to be sort of connected, you know, more to sort of to all these sort of industrial and societal changes. So I would like to thank you all for your participation. And I think, Claire, you know, you might want to say a few more sort of things, but thank you all.
Yes, thank you. Thank you very much. I would like to thank all the speakers and participants and our panelists for this very, very insightful discussion. I don't see any question from the audience. It's a bit slow on participation indeed, but I hope you enjoyed the discussion anyway, and that you have some ideas and an insight to take home to your companies and to your day-to-day job. We have some follow-up events from all the projects. REVamp has an event in October. RETROFEED has the final event. Initiate will continue for another 2.5 years. So there will be plenty more opportunities to discuss all these solutions. But thank you again, everyone, for joining today. Yes, as I mentioned earlier, the recording and the slides will be available on the project's website. So maybe not tomorrow, but check back in a few days if you're interested.
Thanks for the
Thank you.
invitation.
Thank you,
Thank you
Claire.
very much.
Thank you.
Thank you very much.
Bye-bye.
Thank you very much. Bye-bye.